guess we're good to go. Okay, hi everyone. My name is Marcello Balduccini. I'm presenting joint work with Tran from New Mexico State University, Ed Griffor from NIST, and a number of my students from St. Joe's, including Dylan. So this research is on representation and reasoning mechanisms for supply chain, and specifically for supply chain contracts between agents. So the motivation for this work came about, in fact, with the pandemic and the observation of the shortages that we were having during the pandemic, at least in the US. Not sure exactly about Europe, but at least in the US, it started with toilet paper shortages. Then we had much more concerning respirator shortages, or shortages of parts that are needed for respirators for healthcare applications. Chip shortages more recently, which have had an international effect, worldwide effect. But there are also the more, the silly day-to-day things. At the store next to my house over the past month or so, we have been unable to get grapes. And if grapes come in, it's just a few packages of grapes. They disappear immediately. Before that, it was something else. And I'm sure in a few weeks, grapes will be back, and it will be something else that we have a shortage of. So it's, in some cases it's just an annoyance. In some cases it's a much more concerning situation. And supply chain shortages have been addressed in the news, in scientific articles. There's lots of reasons for the supply chain shortages on the technical side, but from a high-level perspective, one of the key ingredients, one of the key reasons for shortages is the lack of resilience in supply chains. So I teach in a business school, and what we do when we teach our students supply chains is we teach them how to extremely optimize, extreme optimization of supply chains, because that's what reduces costs. That's what increases performance of the supply chains. Unfortunately, there is a trade-off between optimization and resilience. If you optimize your supply chain for certain distributors, for certain processes, the moment you no longer have access to those distributors or to those processes, you're done. You need a brand new supply chain, essentially. Second issue related to this that is a key ingredient to the supply chain shortages is the fact that it's really hard to understand how supply chains work. I mean, the high level, yes, we all get, but now you look at a supply chain, existing supply chain, it's difficult to understand all of the dependencies and the ramifications of making a change, of the ramifications of something happening in the world. That's because supply chains are such complex objects that require different levels and different kinds of expertise. And the stakeholders involved, they do have the different levels and different kinds of expertise, but they have a hard time talking to each other because of that. They also have different and sometimes conflicting goals and sometimes conflicting postures, risk-averse versus risk-seeking, for instance. So our goal, ultimate goal, is to develop a methodology to reason about resilience of supply chains. Specifically in this work, we have focused on contracts, so representing supply chain contracts among agents and reasoning about that. At the sort of summary of our contribution is this methodology for representing supply chain contracts among agents. This methodology allows for reasoning about multiple stakeholders' concerns. So the issue I was describing before with differences among stakeholders, that's lessened. It supports reasoning about supply chains as dynamic domains. So the state of the supply chain evolves over time. We can reason about that. And ultimately, the key thing is that it enables identifying issues in the supply chain, detecting if there is an issue, if we're dropping the ball on something, and it allows, the reasoning mechanism allows us to also find mitigations, workarounds for the issues. So at the sort of, as a stepping stone for this work, we have used something that is called the NIST CPS Framework. So NIST, one of our co-authors is from NIST. NIST is the National Institute of Standards and Technology. It's a US agency that is in charge of all standards and a lot of other things, but all standards in the US, similar to the ISO, except on a national level. NIST has observed, has been creating frameworks for a number of years for making the handling of whatever challenges they were focusing on more uniform throughout the US and sometimes outside the US. The NIST cybersecurity framework is used all over the world, for instance. At some point a few years ago, NIST looked at cyber physical systems. So a cyber physical system, you can think of a modern car, definitely a self-driving car, or also an air conditioning system. A cyber physical system is a system that comprises computing components and physical components. Okay, so AC air conditioning system is a typical example. You have the thermostat that has some, sometimes small, sometimes larger computing component. But then there's the whole actual air conditioning devices. Those are heavily physical, right? They put out hot air, cold air. They have lots of sensors, motors, and so on. So that's a kind of, that's an example of a cyber physical system. Cyber physical systems are very challenging to design, maintain, operate, and generally speaking, understand, because similarly to supply chains, they require expertise in multiple different areas. Think of the AC system. As a computer scientist, I may understand how you might program a thermostat, but definitely have no idea of the physics involved, well, almost no idea of the physics involved in the actual air conditioning system that creates cold air and hot air. And so if I were to talk to somebody who's an expert in that area, it would be hard to find the vocabulary that we can share, and we would probably be hard-pressed to find a way to express our overarching goals, because each of us will have our own goals. So that's a challenge in the cyber physical systems industry. And so a few years ago, NIST brought together experts from CPS, and they defined this framework. The framework itself is a complex beast, but for the purpose of this talk, the highlight is that the framework contains a rich hierarchy of concerns. Okay, concerns are things that CPS experts are concerned about: trustworthiness of a system, functionality of a system, performance of a system, and so on and so forth. And so they have created this hierarchy of different kinds of concerns. And this is, while not set in stone, it is intended to be universally applicable to cyber physical systems. You are supposed to find all of the CPS that you need, all of the concerns that you need in it. At the other level of the framework are the requirements. So think of engineering requirements. Here is how I'm going to implement my CPS. I'm going to have encryption, encrypted memory, for instance. Or I'm going to have devices working at a certain speed versus a different speed in my CPS. Why do we do that? Well, there are reasons. For instance, I may want to have encrypted memory because I need confidentiality. I need to preserve confidentiality. And that's exactly a case in which you have a requirement of your system and you're connecting it to one of your concerns. Confidentiality is, in fact, a concern of the CPS framework. So this kind of structure, having requirements and connecting them to the concerns they help address, is provided as this sort of universal vocabulary that helps all stakeholders look at a CPS at a high level and talk to each other about why they have put certain requirements in place, so that experts in other areas can understand it at a reasonable level. Okay, and they can come up with trade-offs on what they should do in which conditions, both in design and in operations. By the way, here you see a very tiny snapshot. Actually, I drew it in PowerPoint. I didn't use the actual diagram from the framework, but that's a little snapshot of a part of the hierarchy of concerns. There are over 100 concerns in this tree. We call that, by the way, a concern tree, somewhat inappropriately. It's actually a forest, and at the top of the forest, the root of each tree is called an aspect. Those are special concerns that are at the root of each tree. The framework is actually just a piece of paper. It's a PDF. Years ago, we started, we took the framework, the CPS framework, and we developed an approach for using ontology-based ontologies for representing the concern tree and requirements, and answer set programming for reasoning about the cyber-physical system and the properties of the cyber-physical system, so that now you can automatically prove properties about your CPS and reason about it. And so when we were thinking of supply chain and supply chain resilience, now coming back to the topic of this presentation, we started thinking, well, supply chain is complex, and we have the problem with stakeholders. That really sounds like what we had in the CPS world. So how about we view a supply chain as a large and complex CPS? After all, there are computing components, definitely, computers, right, controlling the supply chain. And there are physical parts. Just think of the trucks going back and forth, delivering goods one place or another, or everything that's related to producing goods. So that's the first idea that we had. Let's use the CPS framework. Let's view the supply chain as a CPS. And now we can use the CPS framework to provide a clear representation of the dependencies in the supply chain in a way that all stakeholders, remember I was telling you about the problem with stakeholders in the supply chain, now they can all look at this big supply chain and they can talk to each other about why in their specific silo of expertise they have made those choices. So if something happens, the people who are responsible of a certain silo can explain to people responsible for another silo why that requirement cannot be changed, for instance. So that's one piece of the puzzle. The framework, the CPS framework, however, is not enough to deal with supply chains and supply chain contracts. One challenge is supply chains are inherently dynamic. If I deliver goods from one place to another, I have changed the location of those goods. There is a state of the supply chain that changes over time and actions that affect it. So how do we represent the state and its evolution? And for those of you who know me, it's probably no surprise that we decided to use action languages to represent the state of the supply chain. I should also say this is not new, well, to anybody who works in knowledge representation and dynamic domains, but it was also not new to my research group. We had used action languages also to represent the state of CPS. It is a sort of a tried and true approach. So at the core of our approach is action language B, very simple action language. And for those of you who are not familiar, action languages are just formal languages that represent small fragments of English and are aimed at representing simple statements about how the state of a domain evolves in response to the execution of actions. So you have properties, literals essentially, logic of a logic language, that sets of which represent states. And you have three types of statements. Executability conditions tell you which action, that an action can be executed if certain conditions are true in a state. And this is some Boolean expression over properties or literals. Dynamic clause tell you that if a certain collection of states satisfying certain properties, executing an action will cause a certain property to become true or false. Static cause laws or state constraints tell you that in states in which a certain expression holds, then a certain property will be true or false. In action languages and in action language B, there is a precisely defined notion of state, which I already gave you. And then I'm going to skip on the technical details, but you can probably easily see that there is an easy way to define, well, technically complicated, but not conceptually mind-blowing way of defining the notion of transition. Transition tells you if I'm in state sigma 1 and I perform action A, the next state I will be in is sigma 2. And then there's also a way to extend that into the notion of trajectory, which gives you the sequence of states that are traversed by the system if a sequence of actions is executed. So action languages are convenient, and B specifically is convenient for representing supply chains. As a use case, toy use case, we have considered a home building example where people want to build homes. There's a home building company. They need lumber, they need wood, and this wood needs to be, well, cut, prepared in the appropriate way, and then sent, shipped to the home building company. So you have three agents at least: the lumber yard, you have the logistics company, and then you have the home building company. And as a sample of all this, a dynamic causal law can be from action language B can be used to describe the fact that if Z board feet, that's how they're measured, if Z board feet of lumber are delivered to home builder X, then the action by the home builder of receiving that lumber will make it so that now that lumber is available to home builder X. So now home builder X can use it to build. And the other statements about this domain are all representable in action language B. That's not enough though. CPS framework action languages, okay, they come together, they help, and they did in the CPS world as well. Specifically to supply chains, we have one more challenging piece: contracts. In a supply chain, it's all about contracts among agents. So how do you deal with those? How do we represent them? They're a key building block, and when something goes wrong with a supply chain, it's about contracts not being fulfilled. For instance, because a manufacturer had to close. Which contracts have been violated? Which new contracts do you put in place so that everything still works fine, so that all requirements are satisfied? That's a key question. And so action language B is not enough, and therefore we have developed an extension of action language B, which we call LC. The C stands for contracts, which allows us not only to represent the dynamic evolution of the domain, but also contracts and how they're related to it. So in action language LC, a contract is comprised of two parts: the public part and the private part. So the public part, so if we're talking about a contract between two agents, A and B, the public part is what A and B are telling each other. Here is what I commit to. Here is the agreement between the two of us. Public because it's known to both of them. This is the syntax of the statement. So essentially you have an ID, identifier of that specific clause of the contract. A contract will comprise multiple clauses, potentially. A certain agent is responsible for a given goal. This is again a Boolean expression over properties over literals. And there is a time expression that you can put in there: 4 weeks, by week 4, or forever, and so on and so forth. We identify a number of time expressions. I'm not going to go into it. You can find them in the paper. I'm going to focus more on the other parts of this. So by using this statement, you can describe these agreements. But then there is the private part. So internally, each agent will have a reason for having put that agreement in place. And the way we describe that is by a statement of this form, where ref ID is the identifier of a clause from the public part, and raw here is a requirement. Remember, I was talking about requirements before. That's how we actually implement things in our supply chain. So this says that clause is in place because it allows me to satisfy that requirement. I'll show you an example in a second. The private part, as the name suggests, it's not necessarily public to the other agents. It may just be private to that agent. That's why we do it in that way, but the other people don't need to know. Sometimes they shouldn't know. Example of the representation of contracts. using our approach, using action language LC. You can see up here 3 different clauses. L stands for lumberyard, H stands for home builder. This first one, well, and as you can see here, this is a conjunction of propositions. But at the top, the one at the top says that the lumberyard is responsible for producing lumber of a certain quality. There's actually a way to measure quality of lumber. One of my students studied the whole thing, and those numbers are actually reasonable. She did her calculations, which was mind-blowing to me. So by week 4, the lumberyard agrees to produce 144 board feet of lumber of that quality. And also by week 4, it's kind of a repetitive example, but it doesn't have to be, the lumberyard agrees to have the lumber delivered to the home builder. Thanks. And then notice, I don't know if you saw in the picture earlier, but in supply chains, there's also an interesting backflow. So goods will go one way typically, and money goes the other way typically. And so this third statement captures that. It says that the home builder is responsible for paying $122,000 for the lumber that it has received because of the other clauses, also by week 4, because that's when the lumber is delivered. Again, the time points are a little repetitive and boring, but it's just a simple example. So that's the public part. Okay, private part. Why does the home builder want to have the lumber delivered or produced and delivered to them by week 4? Well, because otherwise they cannot build the house, right? Those considerations are obvious to us. They're always obvious. They're always obvious. But then when you have a complex system and something happens, if you haven't captured them, you don't know how to fix it anymore, or you try and then you break something else because you don't understand the dependencies. So the private part captures those dependencies. In particular, C1, and in the paper you'll see there's more to these. In particular, C1 allows us to satisfy a requirement for the home builder called sufficient material for building. What does that mean? Well, satisfying this requirement allows us to address the concern, the time to market concern. This is an actual concern from the CPS framework. In CPS, like in supply chain, you're concerned about getting to market on time. So if you don't address this, if you fail to address this, it means that you are not getting to market on time. You're not producing your home on time, for instance. And in the CPS framework, in the concern tree, I don't know if everybody can read it. There's a little bit of covering here. But the time to market concern is a sub-concern of an overarching aspect, the business aspect. So clearly we're concerned about businesses. So what's important about this example is we have a contract. There are properties, and these are made true or false using based on actions that occur. And so the action language B part of our action language allows you to make these true or false based on actions that are performed. And then on the other side, the private part will take these clauses, link them to requirements, which in turn are linked to concerns. And you have the full picture of why things are in place. I'll obviously skip the semantics. You can find it all in the paper, and I'll just give you the gist. So I gave you the representation. What can we do with that representation? Turns out we can do lots of things, which was our goal. So we can formally reason about our supply chain. We can reason about whether contracts are feasible or not. Company doesn't want to get into a contract if it's not feasible. So we can formally check, given some initial state, can a contract be fulfilled? Ultimately, just to give you the gist, it boils down to computing a trajectory. Actually, trajectories for all the agents involved. It's a little more complicated than that, but a trajectory, for simplicity, that starts in that initial state and satisfies the contract, and in fact, all the clauses at all the points where they're required to be satisfied. Right? We can also similarly, given a trajectory, so actions that have already been executed, we can check if at any point the clause was not satisfied. Because now you have the execution of the actions, you can find the trajectories that correspond to them, and you can check the clauses. And not only you can do detection, but you can also do mitigation, because you can say, okay, but well, from something is not satisfied, some clause. So from this point on, what do I need to execute in order to recover that? And, essentially, it's a planning problem. You come up with the actions that give you the right trajectories. Again, it's complicated because there's multiple agents involved, but complicated but not mind-blowing. And finally, linking to the CPS framework and this overarching level of explanation, which concerns are satisfied given my trajectory. Okay, and that's also easy to do. You have trajectories. You connect them to clauses, as I showed you before, that are here, that are satisfied or not. The clauses are connected to requirements by the private part of the contract, and then you get to concerns, and you can say, well, look, the trustworthiness of the supply chain is not satisfied, or confidentiality, or the functionality, something is really broken in that case. And we can detect, but also we can mitigate, similarly to what I said up here, right? We can also mitigate. You just need to find new trajectories from this point on. All of this, I sort of downplayed it a lot for sake of time, but all of this is also implemented in answer set programming, as kind of obvious when you're dealing with action languages. So we can actually directly run and solve these problems. And so just to conclude, so highlights of the contribution. So we have come up with a methodology for representing supply chain contracts, reasoning about them. It leverages existing building blocks. That is a good thing in this case. The CPS framework, which helps with stakeholders' concerns. Action languages, so we can reason about the dynamic domain underlying the supply chains. It's implemented in ASP. It allows us to, key thing in my mind, explain why things are broken and explain why things, the reason for why certain corrections are expected to work, thanks to this level of concerns. And we can explain it to everybody, not just technical people. We can explain it to C-suite people, CEOs. In terms of future work, we've tested it on small toy examples. We need to test it on realistic examples. It's going to be fun. We just need to find the time to do that. It's supposed to work. And we are currently working on an actual system. So not just the ASP implementation, but an actual graphical user interface that non-technical users or non-ASP or declarative language users can use to represent the supply chain and to work with it. That's it. Any questions?
Maybe I have a question concerning the examples. You mentioned you tested only on small examples. What do you expect if you tested on realistic example? Is it just a matter of work, or would it be also an efficiency problem of your approach?
I expect everything. Yeah, I've been in in this area for quite a while by now, so I know more or less what I'm concerned about. So performance, definitely. I mean, these supply chains are large. If it all depends on at which level you represent things, right? If you have 5 contracts because you're taking a very high level and 3 agents, it's going to be fine. But big concern I have. Oh, and I should have mentioned. So action language B is all based on discrete states. Everything is discrete. Well, in an actual supply chain, not always you can have simple, nicely separated discrete states. So I have numbers involved, constraints on numbers, more than 3 levels of quality. Performance can be a bottleneck, especially if domain experts can just dump whatever they want in their tool because they don't, we are used to it. We go, oh no, I shouldn't write that. I shouldn't put all that stuff in. They're going to put everything in there. But that's what we need to do, and we'll address the challenges, potential performance challenges when they come in. Questions?
Thank you. Could you use this approach to perform causal and counterfactual reasoning? And can you ask questions like what happens if the delivery of the lumber is late and what that does to the schedule and everything else?
Yeah, yes. So So the answer is absolutely yes. Actually, very interesting and very exciting. That's sort of the direction where my mind always goes. One part of it is relatively straightforward. What happens if the delivery is late? It's not difficult to come up with trajectories that correspond to the delivery being late, and then you just check the properties corresponding to those trajectories. Counterfactual reasoning is more intriguing to me. I would expect that it is possible, but that's not something I thought about very, very carefully. But we've done some counterfactual reasoning work many years ago, not on this. And my inclination would seem to be, well, once I can define the trajectory properly, as I can do here, then counterfactual reasoning is doable. But I cannot guarantee that.
Thank you.
I think we are out of time now. Thank you very much, Dr. Balduccini, for your
Thank you very
great
much, everyone.